So this is now the third video on a continuous functions. Not really continuous in and of itself, but hey, so we're going to take a look at the last and final thing. With continuous functions, things are continuous. That means you can draw them without lifting up your pen. As soon as you lift up your pen, that's a point of discontinuity. So this whole video is going to take a look at those points of discontinuity and what they look like, because they do have specific names, and you do need to know the names of all of the types of discontinuous functions. And then kind of the stuff that you can do, both algebraically and graphically, just to kind of see that that is what they are. So this video is simply going to be on all the types of discontinuity and what that looks like. Okay, so there are three types. So we're going to go through, we're going to graph those three types, and we're going to kind of talk about what makes each one of them. So I'm going to show my window again. Again, it's just going to be my note sheet. And I think it's going to be somewhere around the 21st. Okay, and today is on types of discontinuity. Okay, so there are three of them. So we're going to talk about all three types. So the first one is the one that you have seen most often, and we have actually started doing some work with it. So the first one is the hole in a graph. Okay, so graphically, you should kind of know what that looks like. So if we're going to talk about a hole in the graph, so graphically you would have something going like this. It would go, there would be a space, and then it would continue on. Okay, so this is one type of discontinuity. This is the only one that we actually call removable. Okay, what removable means is you can algebraically remove the problem and calculate the limit. Okay, so if something is a removable discontinuity, that means you can actually calculate it using some things, and you can remove that problem thing, so you can calculate that limit. We have several ways of doing this. You guys are probably pretty familiar with them because we just finished studying those. So what the three ways are is you can factor to remove the discontinuity, and you can calculate it. You can rationalize, or you can simplify. Okay, so if you have a discontinuity that is a hole or a gap, you can do one of those three things, and you can remove that discontinuity. Okay, now we also need to look at this thing from the perspective of a limit. Okay, so if you remember, the limit has three parts to its definition. So what I'd like to do is I'd like to take a look at those three parts and talk about what it looks like and how you know, given that information, that it is a hole in the graph. So first of all, let's call this point right here, just like we usually do. Let's call this C, and let's call the point where this is, let's call the value at that point is L. Okay, so let's take the limit as x approaches C from the left of, and let's call this function f of x of f of x. So we come in from the left. Okay, we notice that it has a value of L. Now, remember, you also need to find the limit as x approaches C from the right of f of x. Okay? So let's take this. Let's come in from the right. We notice that the value is L. Now, the last thing is you need to find the value of the function at that point, and you'll notice that there's a hole there. So it is undefined. So how do you know, using the limit definition, why you have a hole there? There is one key feature, okay? The limit from the left equals the limit from the right. The problem is the value does not equal the limit. So whenever you have a hole, this is what's always happening, okay? If you have a hole, that's what your limit looks like. You will have the two limits coming in from the left and the right equaling the same number, but it will not equal the value, okay? Now, let's look at the other types of discontinuities. The second type of discontinuity is B. The second type is an asymptote. In this case, we're going to talk only about a vertical asymptote. Okay, so let's talk graphically what that is. So we'll make a little graph over here. We know that there's going to be some sort of line at C, and then the graph is going to go here, and then maybe the graph is going to go down here. But you'll notice that it just never crosses that line. Okay? Now, there's something you need to know about this one. First of all, this is non-removable. Okay? What that means is you can't algebraically remove it. You can't algebraically remove this space. Okay? If you remember when we took a look at the rational function, when you factor it, it's one of those things that does not cancel out. So if we have something like this, x plus 3, anything that's still left in the numerator or in the denominator after you cancel stuff out, those would be your asymptotes. That's where they're located. You can't take those away. They are not removable. Okay? So let's talk, though, what this looks like and what you always see. So whenever you have this type of discontinuity, we still have to look at it from the left and from the right. So let's take the limit as x approaches c from the left of the function, which is f of x. So this function is f of x. Now, notice, there's always something that's true about asymptotes, okay? As you approach from the left, its value is either positive or negative infinity. That tells you that it is going to be an asymptote. It doesn't go to a value. It goes to either positive or negative infinity. Now, you also have to look at this as it comes from the right, okay? So as we look at this, we trace the right as we get closer to C, and you'll notice that f of x equals negative infinity. This is what you see when you have a vertical asymptote, and we talk about it in terms of continuity. Both limits, as you go from the left and the right, go to some form of positive or negative infinity. Now, the final thing, of course, is f of c. And you'll notice if it's an asymptote, that should not exist, okay? So this is the key feature of an asymptote. So when you see an asymptote, here's what you should see. If it's an asymptote, you will always see the limit as x approaches c from the negative side, and the limit as x approaches c from the positive side equal positive or negative infinity. You will also notice that f of c does not exist. This is what a limit or this is what continuity at an asymptote looks like. It's always some form of this. Okay? Now, we have one more type of discontinuity. That last type of discontinuity is, it's called a non-removable or a jump discontinuity. Okay? So the third and final one is called a jump discontinuity. Now, this one usually, it's called a jump discontinuity. It usually occurs in piecewise functions. Okay? Now, I do need to state to you that this is also non-removable. You can't do some sort of algebra to get rid of it. Okay? So you have to, you just assume that it's there and you can't get rid of it. So let's draw a graph that has a jump discontinuity. Now, you've seen them on something. So a jump discontinuity kind of goes like this. So it'll maybe go to here, then we'll have a dot, and then it'll come down to here. Notice that there is a jump between those 2 points. So this will be C, and let's call this L, and let's call this K. Okay? So let's take a look at a jump discontinuity in terms of the definition of continuity. So if we take a look at the limit as x approaches c from the left of our function f of x, notice as we approach from the left, the value is k. Now, we also need to find the limit as x approaches c from the right of f of x. And notice in our graph, as we approach from the right, notice the value is L. Okay? And then we have to find the value at C. Okay? So let's find the value of f of C. And we notice in this case it is L. How do you know that that's a jump? Okay? What you're going to see every time you see a jump discontinuity, you will notice the limit as x approaches c from the left of the function is equal to some number. The limit as x approaches c from the right is another number. But you also will notice that f of c equals either k or L. It doesn't matter which one. It's just where you end up putting the closed dot. So in a jump discontinuity, the limit from both sides ends up being different values. Okay? So that is what defines a jump discontinuity. So our 3 types of discontinuities, as you can see, our 3 types of discontinuities, we have a removable one, which allows us to do some algebra to get rid of it. We have asymptotes or vertical asymptotes where both limits go to infinity, but the value is undefined. And our last one is a jump discontinuity. You notice both in the left and the right, they go to a certain value, and they're both different. And then the value of f of c is either one of those 2 values. So those are our types of discontinuities, and we will apply that stuff in class on the next couple of days. I hope you have a good one, and I will see you again later.